Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 54. In this lecture, we'll discuss change in entropy. This topic is covered in Chapter 22 of our textbook by Surway and Jowett. In our last lecture, I introduced you to the concept of entropy and how it is used in the second law of thermodynamics. Before doing some practical calculations with entropy, let me just review what we learned last time. We learned that entropy is equal to the Boltzmann constant times the natural log of W. In this context, W is the number of microscopic configurations or arrangements or states that a system could possibly be in. Don't confuse W with thermodynamic work. Here W stands for an entirely different concept. It counts the number of microstates. W is a unitless quantity, so the natural log of W is also unitless, and therefore the unit for entropy is determined by the unit of the Boltzmann constant. Recall that the Boltzmann constant has units of joules per Kelvin, and so the SI unit of entropy is also joules per Kelvin. You should think of entropy essentially as a measure or an accounting of the number of microscopic states that a system could possibly be in, consistent with its large-scale description in terms of pressure, volume, and temperature. When we say that a system has a large entropy, what we're really saying is that it has many microstates that are available to it. The reason I say many is because when you take the natural log of a number, you get a much smaller number. So if S is already a large number, then W must be a tremendously enormous number. The second law of thermodynamics can be stated in terms of entropy. It essentially states that for an isolated system, the change in entropy must be greater than or equal to 0. This is often interpreted as saying that a system tends to maximize its entropy. Entropy is maximized because the system seeks the state with the largest number of microstates. The largest number of microstates is the macrostate that is most likely, so the system naturally tends towards a state that corresponds to the largest number of microstates. We can state this a little more mathematically by differentiating both sides of this equation to find that a change in entropy is equal to Kb over W times the change in the number of microstates. So when we say that a system is increasing its entropy, what we're really saying is that the system is trying to increase the number of microstates that are accessible to it. Unfortunately, the equations on this slide are not very practically useful to us. Although they help us understand entropy and changes in entropy, from a practical point of view, calculating W or dW for a realistic system is prohibitively difficult. In other words, for a system with more than 1,000 atoms, let's say, calculating the number of microstates that are available by enumerating them in a table, for example, is simply too difficult to perform. So what we really need is another set of equations that help us to perform practical calculations with entropy. We turn to this challenge on the next slide. As it turns out, the actual value of entropy is usually not very important. What is important is the change in entropy. So often S by itself is not important. What is important is delta S. In this respect, entropy is similar to energy. Recall from your course on mechanics that we don't always care about the actual value of energy for a system. What we usually care about in solving problems is the change in energy, simply because in using conservation of energy, it's the change in energy that must be equal to 0. Similarly, we don't always care about S. What we really care about is delta S, or the change in entropy. So what we need is an expression for delta S. It turns out the change in entropy is related to the amount of thermal energy that is entering or leaving the system. A little more precisely, when an infinitesimal amount of heat, call it dq, is added to a system at temperature T, the infinitesimal change in entropy is equal to dq divided by T. I'm not proving this formula to you. For the time being, you'll simply have to believe me. Now, this formula is valid for an infinitesimal amount of heat. If a larger amount of heat is added or subtracted to a system, then we simply integrate this formula. So the change in the entropy is equal to the integral of dq over T. Now, if T happens to be a constant, for example, in a phase change, for example, when ice melts to water, then we can take T out of the integral, and then the integral of dq is simply Q, which is the total amount of heat that was added to the ice to melt it. However, in general, T can change throughout a process. For example, in an isobaric heating of cold water to warm water, T can be a variable itself. And therefore, in evaluating this integral, we have to either express Q in terms of T, or we have to express T in terms of Q. So evaluation of this integral can be a little bit tricky, and we'll spend the rest of this lecture looking at some examples that will help us understand how this integral can be used. Let's begin with a relatively straightforward practice problem. Suppose n moles of a hot diatomic ideal gas is initially at volume VI and pressure PI. The pressure of the gas is changed to PF in a reversible isochoric process. Calculate the change in entropy of the gas. Note that we're not given any numerical values here, so what we're really looking for is an expression for the change in entropy in terms of variables that are given to us in the problem. If you want, you can pretend that we have numerical values for N, VI, PI, and PF, and what we're looking for is a formula for delta S in terms of those variables. Now, it helps to read the problem carefully because there's a lot of hidden information here. First of all, we're told that this is an ideal gas, which means it must obey the ideal gas law. At this point, it may not be obvious why this would be useful, but it helps to make a note of it, maybe even write it in the margin of the question in case you need it later. We may also need to know the fact that this is a hot diatomic ideal gas. That tells us that the degrees of freedom for this gas is 7. In other words, each molecule of this ideal gas has 7 ways in which it could store energy. We're also told that the process is a reversible isochoric process, which means it's one of the 4 fundamental thermodynamic processes that we've studied. If you want, you can represent such a process on a PV diagram by a graph that looks like this. So the volume doesn't change. Whatever it is at the beginning of the process, it remains that throughout the process, and we represent something like that by a straight vertical graph as shown here. Now, the volume doesn't change in an isochoric process, but you should remember that the pressure changes, and because it must obey the ideal gas law, the temperature must also change in such a process. We can now begin to calculate the entropy. We start with our expression for the change in entropy. The change in entropy is equal to the integral of dq over T. Now, this is not a phase change process. This is a temperature change process. And we remember that whenever the temperature of something changes, the amount of heat required, Q, is given by this expression here, where N is the number of moles or the amount of substance, C is the molar specific heat capacity, and delta T is the change in temperature. We're now essentially using the infinitesimal version of this formula, which says dq is equal to nc dt. So essentially, I'm replacing this dq by nc delta t. Notice that you have to be a little careful because there are different kinds of specific heat capacity. We're using the isochoric specific heat capacity, or C sub V, in this process. Now we can evaluate the integral. N is a constant, we can bring it out of the integral. CV is a constant, so we can bring it out of the integral. The integral of dt over t is simply the natural log of t. Of course, we have to substitute the limits of integration. Notice that the limits of integration should match the variable of integration. So if we're integrating with respect to temperature, then we need to know the initial and final temperatures. When we substitute in the limits of integration, what we get is NC natural log of TF over TI. Now, TF and TI are not given to us, but using the ideal gas law, we can show that TF over TI is equal to PF over PI. A little more precisely, you can say that according to the ideal gas law, TF must equal to PF VF over NR, and T sub I must equal to PI VI over N times R. And because this is an isochoric process, VF and VI must be equal to each other. So you can now see that TF over TI must be equal to PF over PI. We're not done yet because at this point we don't know what the specific heat capacity of this gas is. However, we recall that for an ideal gas, the specific heat capacity, at least the isochoric specific heat capacity, is equal to D over 2 times R. And D, of course, as we said earlier, is 7. So now we can say that the change in entropy is N times 7/2 times R, which is the gas constant, times the natural log of PF over PI. At this point, we have a formula in terms of variables that are given to us in the problem, and so we can say we are done. Let's now solve a slightly more challenging practice problem. Suppose n moles of a hot diatomic ideal gas is initially at volume VI and pressure PI. The volume of the gas is changed to VF in a reversible isothermal process. Calculate the change in entropy of the gas. So once again, we don't have any numerical values. What we want is an expression for delta S in terms of variables given to us in the problem, such as N, VI, PI, and VF. Once again, we know that this is an ideal gas, so it must obey the ideal gas law. We know that it's a hot diatomic ideal gas, so the number of degrees of freedom is 7. But this time, the process is an isothermal process. This is another one of the 4 fundamental thermodynamic processes that we've studied. In this case, the temperature remains constant, but the pressure and the volume change throughout the process. We start with our usual expression for delta S as the integral of dq over t. Since this is an isothermal process, we know the temperature remains constant, which means we can take t out of the integral. So now we have 1 over t integral of dq. From your calculus class, you should know that the integral of dx, for example, regardless of what x is simply equal to x. So in this case, the integral of dq is simply equal to q, which is the total heat that leaves or enters the system in this isothermal process. Unfortunately, at this point, we don't have a simple way of calculating q. You might recall that in our previous practice problem, we used this expression, q is equal to nc delta t. This expression is valid for an isobaric process. It's valid for an isochoric process. However, it is not valid for an isothermal process. An isothermal process is by definition a process in which the temperature does not change. So you're not allowed to use this expression here. To calculate Q, we need something else. What we need is the first law of thermodynamics, which tells us that the change in the internal energy is equal to Q plus W. We also know that according to the equipartition theorem, delta E internal is equal to the number of moles times the number of degrees of freedom times 1/2 R delta T. Since this is an isothermal process, delta T is equal to 0, which means this is equal to 0. Now, combining these two equations together, we find that Q must equal to minus W. So any heat that enters or leaves the system must be directly related to the work that is performed on or by the system. So at this point, we can replace Q with W, more precisely by minus W. We're doing this because we know how to calculate the work performed in an isothermal process. In a previous lecture, we calculated the work in an isothermal process, and we found that that work is equal to minus nRT natural log of Vf over Vi. You can now see that the T's cancel out, the negative signs cancel out, and what we're left with is nR times the natural log of Vf over Vi. Since now we have an expression in terms of variables given to us in the problem, we're done with this practice problem. Let's end this lecture with a challenging practice problem. 3 kilograms of ice at 0 degrees Celsius is placed on a table in a room at 20 C. The ice melts and eventually comes to thermal equilibrium with the room. The room temperature does not change. Given this information, calculate the entropy change of the ice, calculate the entropy change of the room, and finally calculate the net entropy change. For this problem, you may need the following constants. The heat capacity of water is 4,186, and the latent heat of fusion for ice is 3.33 times 10 to the 5th. As usual, it helps to read the problem carefully. There's a lot of hidden information here. First of all, note that we have essentially two systems in this problem. One system is the ice, and the other system is everything other than the ice. So essentially the environment of the ice, which we'll refer to as the room. Now, since the room represents everything other than the ice, since it represents the large environment, we're going to treat the room as if it's a heat reservoir. More precisely, we're going to assume that the properties of the room don't change as a result of this small piece of ice melting. A little more precisely, what I'm telling you is that the final temperature of the room will be equal to the initial temperature of the room, which was equal to 20 degrees Celsius. We're also told that the ice, after it has melted and warmed up, reaches a thermal equilibrium with the room, which means that the final temperature of the ice will equal to the final temperature of the room, which is equal to 20 degrees Celsius. So we have lots of information about the final temperature of the two systems that we want to consider. With this information, we'll first calculate the change in the entropy of the ice, and then calculate the change in the entropy of the room. Once we have those two, we can simply add them together to find the net change in entropy. Let's start our calculations by considering the ice. Now note that there are two things that are happening to the ice. First, the ice melts and then it warms up. So during stage 1 or step 1 of this process, what we have is a phase change at a constant temperature, and then in step 2, the temperature is changing while the phase remains constant. So we'll calculate the change in entropy of the ice in 2 steps. Step 1 involves a transition of ice at 0 C to water at 0 C. So we're just talking about the melting of the ice without a temperature change. If you want, you can think of this as an isothermal process. The change in the entropy of the ice for this first step is equal to the integral of dq over T. Since the temperature is constant, we can bring it out of the integral. The integral of dq is simply q. Now we are talking about a phase change here, and we know that for a phase change, the amount of heat that is necessary is equal to the mass of the substance times the latent heat. Both of those numbers were given to us in the problem. Multiplying them out, we find that the amount of heat that is necessary to melt the ice is 999,000 joules. Now the temperature of the ice is simply 0 degrees Celsius, but of course we need to convert that to Kelvin, which is 273.15 Kelvin. Plugging these numbers into our calculator, we find that the change in entropy of the ice in this first step is approximately 3,657 joules per Kelvin. We now look at the second stage. In this stage, the ice has already melted, and what we have is cold water that is going to warm up. So we're talking about a transition from water at 0°C to water at 20°C. Notice there's no phase change here, only a temperature change. Once again, delta S is equal to the integral of dq over t. Temperature now is not constant, so you cannot bring it out of the integral. We know that for a temperature change, Q is equal to mc delta T. We want to use the infinitesimal version of that equation, so we're going to replace dq with mc delta T. The mass and the specific heat capacity are constants, so we'll bring them out of the integral. The integral of dt over t is simply the natural log of t. When we plug in the limits of integration, we find mc times the natural log of tf over ti. Ti is 0 degrees Celsius, Tf is 20 degrees Celsius, but of course, once again, you have to convert those numbers to Kelvin. Once you do that, you can plug the numbers in and find that the change in entropy of the ice for this second step is approximately 887 joules per Kelvin. So now we can add these two numbers together to find that the net change in entropy of the ice throughout the whole process is approximately 4,544 joules per Kelvin. That answers part A of the question. We can now turn to the room. The net change in entropy of the room is given by the usual formula, integral of dq over t. Recall that we're thinking of the room essentially as the environment, as everything outside of the ice. So we're talking about a very large system. For such a large system, the temperature does not change. So T is a constant, which means we can bring it out of the integral. The integral of dq gives us Q. So now at this point, we need to calculate Q for the room, and this is a slightly tricky problem to do. Notice that we cannot use the formula Q is equal to mc delta T. Firstly, we don't know what the mass of the room is. Secondly, we don't know what the specific heat capacity of the room is. And lastly, the temperature of the room does not change. It's an isothermal process, so we're not allowed to use this formula to calculate Q of the room. So what we have to do is calculate Q indirectly. We basically use conservation of energy. We note that the ice is melting because it's absorbing thermal energy from the room. In other words, heat is leaving the room and entering the ice, causing it to melt and eventually to warm up. So any output of energy from the room must equal an input of energy into the ice. A little more precisely, we can say Q of the room is equal to minus Q of the ice. If the ice gained, let's just say 10 joules of energy in the process of melting, those 10 joules must have come from the room or from its environment. So we can say that the room lost 10 joules of energy. We represent that by minus 10. Now, what is the amount of heat that the ice acquired in this process? Well, it's a two-step process for the ice. In the first step, there is a phase change, so the amount of thermal energy that enters the ice is ml in step number 1. And step number 2, it's a temperature change process. The amount of heat there is mc delta T. We have all these numbers, we can plug them into our calculator, and we find that while the ice is melting, the room is losing 999,000 joules of energy. And while the water is warming up, the room is losing a further amount of energy equal to 251,160 joules. We also need to plug in the temperature. The temperature of the room is given to us as 20 degrees Celsius, but of course we need to convert that to Kelvin, which is 293.15. When we put it all together into our calculator, we find that the change in the entropy of the room throughout this whole process is minus 4,264 joules per Kelvin approximately. That answers part B of this question. Answering part C is easy. The net change in entropy of the ice room system is simply the sum of the two numbers that we found before. We find that the net change in entropy is approximately 280 joules per Kelvin. Now notice that the room and the ice together essentially represent the entire universe. What we're talking about here is the ice and then everything other than the ice. We're calling it the room, but you can also call it the environment or pretty much the rest of the universe. So what we're finding here is that the net entropy change of the universe is a positive number. This is reassuring because the second law of thermodynamics tells us that for an isolated system, the change in entropy must always be greater than or equal to 0. And the universe can be viewed as an isolated system since we don't believe there's anything outside of the universe. If there was something further, we would just expand our definition of the universe to encompass it. So the fact that delta S for the room ice system is a positive number is reassuring. And that is the end of this lecture. Thank you for your attention.